Welcome. In this video I'll discuss in a bit more detail the Hall MHD terms and the effects they have on some phenomena we're interested in. So things like magnetic reconnection, the dispersion of waves, so whereas in ideal MHD waves have a particular velocity, so there are things like sound waves or alpha waves for example, but they typically always travel at the same speed regardless of their wavelength, whereas Hall MHD terms introduce dispersion, so that different frequencies travel at different speeds. And this, for example, gives rise to the Whistler wave, because the low frequency waves would travel slower than the high frequency waves. And so when waves were excited in the atmosphere by things like lightning storms, the high frequency would arrive first, and so they'd appear like a whistling, downwards sweeping whistle. And so this has various interesting and useful effects. There's also a related term called the Biermann battery, which may be important in generating magnetic fields, for example in the early universe, but it's also used in current day experiments. So this is the terms we're looking at are these terms in the Ohm's law. So there's this, here we have the ideal MHD terms on the left hand side. So in ideal MHD this right hand side is 0, and now this is the ion flow. Essentially this is the fluid flow, so it's weighted by the mass, so it's mainly the ions. This here is the current, and so when this term is added to this term, it means that the magnetic field is not frozen into the ions, but it's frozen into the electron fluid instead. So this term here, J cos B, this means that the magnetic field is frozen into the electrons. So whereas in ideal MHD we have the E plus V cross B is 0, and so the magnetic field moves at the ion flow speed u. When we add these terms, we end up with this equation. So we have E plus, now we have the VE, so it's the electron fluid flow, cross B. And then here on the right hand side, we just have the minus the electron pressure term. So this term breaks frozen in completely, whereas this J cos B term just means it's frozen into the electrons rather than the ions. And so both these terms can be very important in magnetic reconnection. So magnetic reconnection is important in many areas of plasma physics, so astrophysics and solar physics, but also in tokamaks as well. There are some examples of where tokamak reconnection is important. So one, for example, is in startup. There's something called merging compression, which is used in starting up some tokamaks. And essentially you do it by creating two nested flux surfaces. So you have currents like this, so you might have breakdown around two coils for example, and you create a set of nested flux surfaces. So this would be like the center of the machine here, this would be like major radius here, and you have two currents basically running in the same directions. This is current running into the page, for example, J into the page, J here into the page, as we created magnetic fields like this, and this is running like that, and then these two currents move towards each other. You have currents in the same direction, so they attract each other, and what you end up with is a reconnection region in the middle. So you have a region where you have like this, and this one has moved up here, and you end up with a narrow layer here in the very center, because at this point the field is changing direction. So you have field changing here from left to right here to right to left, and in the middle we form this very narrow layer where reconnection occurs. And what's happening here is that flux is moving into this region from top and bottom and being ejected out the sides here, and so you form flux surfaces around the whole thing. So you end up forming one set of nested flux surfaces at the end, because you take these flux surfaces from the individual currents here, reconnect, so you take these field lines and break them and diffuse them across this narrow layer, and eject them out the end and form this single set of flux surfaces. And so this is a merging and compression process which involves reconnection. And so this is generally at quite low temperatures, so tens of eV maybe, because this is during startup, so just the very beginning of the plasma. But we also see reconnection at very high temperatures. So an example is sawtooth crashes. So I discussed this in an earlier video. Essentially what's seen on soft X-ray signals, this is time, this is soft X-ray, this XR. You might see X-rays increase, then crash, increase and crash, crash. And what's seen on things like Thomson scattering, so if you plot this as distance, let's say major radius, so taking a slice through the plasma, you might plot, for example, the temperature. So we have the core of the plasma in here, and then major radius, so we're taking like a slice through the plasma. What you'll see over time is that this is basically modified so that you can produce this kind of thing here, where this very rapidly forms a kind of oscillating region in the middle, and then this very quickly crashes. So this whole thing kind of crashes down in the middle. And what's thought to be happening is you start with a set of nested flux surfaces like this. The innermost flux surface has Q a bit less than 1. So you might have a surface here where Q equals 1 in plasma, and so Q is a bit less than 1 inside here, and these become essentially unstable. So you form this kind of very elongated and one-sided, this kind of helical pattern of flux surface in the middle, and you end up with reconnection occurring, and essentially the hot plasma in the core can very quickly flow out through the reconnection region, and the temperature can drop very quickly. And so this occurs when plasma is very high temperatures, so keV kind of levels, and yet this crash can still occur on very short timescales. And so you can start to look at which terms might be important. And the usual one, which it was originally proposed for reconnection, is resistivity. So we just have resistance in the plasma, so collisions, and this has some timescale, but you can see when this is important by looking at the Lundquist number. So in the previous video we worked out when resistivity should become important, where here v is a typical velocity like the Alfvén speed, L is the length, so it's like the width of this reconnection region here, or in merging compression it's the width of this. It's a very small distance, is this width here. You can see how small that needs to be for resistivity to have an effect. So that's the resistance of the plasma. This is the Lundquist number S, and that should be about 1 for resistivity to be important. And if you take typical values, say eta is roughly, so if you use this simple formula for Spitzer resistivity, you get that this is roughly 3 × 10⁻⁸ ohm meters at about 1 keV. So at T is about 1 keV, which is kind of a core temperature maybe relevant for sawtooth. And if you can work out what, say, the typical velocity is, so if the Alfvén speed, so if B is roughly 5 Tesla, something like eta, a density of like 10 to the 20 meters cubed. So this gives you an Alfvén speed of around 7.7 times 10 to the 6 meters per second. And so you can use this as typical V. So we now have value for eta, for V, and so we can work out what length this should become important. And this gives the typical length scale when resistivity should become important is like eta over mu naught. It's Alfvén speed. This is like 3 nanometers. So these length scales are extremely small when resistivity here becomes relevant or becomes large, and so you need to form extremely small structures for this to become important. By comparison, the Hall terms, so if you compare this to the Hall terms, So these become important when the ion skin depth or the ion inertial length becomes comparable to your typical length scale, and this delta is roughly 2 centimeters if n is about 10 to the 20 per cubic meter. And so whole terms, including the electron pressure term and the J cross B term, become important far before the resistance does, at least at core tokamak cone temperatures. And so this is essential. So whole terms are essential for describing this kind of high temperature reconnection. Okay, so another area that whole terms are important is in wave dispersion, so dispersive waves. So in ideal MHD, the most waves travel either at sound speed or the alphane speed, so you get the fast and the slow magnetosonic waves. But those wave speeds don't depend on the wave number. So here we end up with waves which depend on wave number, wave speeds which depend on their wave number. So here some waves are things like Whistler waves, which were first found in the atmosphere. So radio signals, for example, and also kinetic alphane waves. And so the dispersion relations, at least for right-handed waves, look a bit like this. So we have this is like parallel waves. So these are running along. So K is parallel to B. So the B field. So the waves traveling along the magnetic field, and these are right-handed. So it matters whether the waves are polarized to the right or to the left, because of the direction of the ions and electrons. So we write down here's the frequency. And so if you have here we have the ion cyclotron frequency. Here we have the electron, and we get E like this. And so normally we'd have, say, the alphane speed, the alphane like that, and we have the light wave which runs like this. So this would be C, like the light wave. And what we have when we have whole MHD is you end up with a wave which kind of starts like the alphane wave at low frequencies, and then transitions up to higher frequencies, and then tails off around the electron frequency. And this is the Whistler wave. And then we have a cutoff around the electron frequency. So this is where the wave is resonant with the electrons and so is absorbed. But a little bit above the electron frequency, you end up with another wave which travels up like this. And this is the normal light wave. So you have this kind of cutoff effect at the electron frequency. Okay, so this Whistler wave has a frequency, depends on K, and this shape means that the waves travel at different speeds if they have different wavelengths. In particular for Whistler, the longer wavelengths travel slower. So we have that the speed, the group speed, which is like the d omega by dk, is proportional to square root of omega. And so the higher the frequency, the faster the wave moves. Okay, so lastly I want to discuss a term called the Biermann battery. And this is a way of generating magnetic fields without needing to start with any magnetic fields. This is different from ideal MHD, for example, where the MHD induction equation contains, for example, just d by dt of the magnetic field is V cross B. And so if you have no magnetic field to start with, there's no way of generating magnetic fields. The Biermann battery is a way of creating magnetic fields without having any at the beginning. So it depends on the electron pressure term in Ohm's law. So we have E plus the fluid velocity. So this could be electron, fluid, or ion. Here it doesn't really matter, depending on whether the J cross B term is included. And then here we have the electron pressure term. Here we're just assuming a scalar pressure. So it's the electron pressure term in Ohm's law, and then we substitute into Faraday's the induction equation. So you have the usual ideal MHD term. So we have a curl of U cross B. So if this is from ideal MHD, if B is 0 at the beginning, then it stays 0 for all the rest of the time. And so in ideal MHD, there's no way of creating magnetic fields unless you already have a magnetic field. And so there are dynamo effects for creating or enhancing the magnetic field, but there's no way of creating a new magnetic field. And so there's a long-standing problem of where the magnetic field came from in the universe, and one of the possible explanations is this extra term here from the electron pressure. So we have this gradient of extra pressure over En. And on this term you can rearrange, and this term just becomes grad N and so here you have the curl of the gradient obviously is 0, and so the only term that's left over is here you have a gradient of N, and you just differentiated this to get N squared, and so there's grad N cross grad P. So if you have the gradient of the density and the gradient of the pressure in different directions, then you can generate magnetic fields. And so you can generate magnetic fields without any to start with. So you just need to have this mismatch between the gradients, and you end up creating magnetic fields. So this is used as a possible explanation for where the origin of the magnetic fields in the universe, and also is used in experiments to create magnetic fields. So particularly in laser plasmas, quite often using high energy lasers onto a target, you can create these situations where you have very strong density gradients and very strong pressure gradients, and these can drive currents and create magnetic fields. So these is three major areas where the whole MHD is important, and these terms, so the electron pressure term or the J cross B term, can make a big difference to experimental observations, and can be important to include in models.